Hey everyone, Mrs. Hilt here with Newton's third law of motion. Please follow along with your Newton's laws worksheet. You guys will be on the second page and we will be able to get through number 17C with this lecture. You'll get further information about what to do with the other problems very soon. All right, Newton's third law of motion. This is the action-reaction law. And it is often stated that every time there is an action force, there is also a reaction force that is equal in size and acts in the opposite direction. So our objective with these notes is to understand that forces do come in pairs of equal magnitude and that they act in opposite directions. Okay, so this law can be a little hard to understand, but Newton's cradle, this desk item that you guys have probably seen at some point, in maybe a gift shop or on a desk, uh, this demonstrates Newton's law perfectly, and it's actually Newton's cradle, the name of it, for a reason. So we can easily see how the forces are acting in pairs. One force is applied to one side, and the exact opposite direction has another force being applied to it. So when there are three balls that are pulled back and left to bounce, then three balls on the other side do the same thing. Or when one ball is pulled back and let go, one ball on the other side ends up flying up on the other side and with the same force, but in the exact opposite direction. So unfortunately, all examples aren't as easy to see Newton's third law as Newton's cradle. For example, these three examples. How on earth could a person touching their phone or sitting at a desk or hitting a baseball represent equal and opposite forces in the opposite direction? All right, I want you to first, let's look at the person sitting in a desk chair. What forces might be acting here? Pause the video and think about what could be the action force and what would be the reaction force. When you're ready for the answer, press play. All right, so for this example, the person's bottom pushing down on the chair, that is the action force. She sat down there. And the reaction is the force of the chair pushing back up on her because she's not crashing to the ground. That there is a force holding her up and they're just balancing each other out. All right, how about this one? So again, look at the picture and try to identify what the action force might be and then what the reaction force might be. And just think about it, maybe say it out loud. When you're ready for the answer, press play. All right, so the action force would be the finger pressing on your phone screen or your finger pressing on your phone screen. And the reaction force is actually just the phone screen pushing back on your finger. It seems kind of odd, but there has to be a force pushing back from the phone. Otherwise, your finger would go straight through your phone. Just like your finger could just like go flying through the air, like when you're going to give somebody a high five. There's something stopping your finger from going through your phone. Therefore, there has to be a force being applied by your phone on your finger. All right, and the third one, a person hitting a baseball. So again, think about what the action and reaction forces might be. When you're ready for the answer, press play. Okay, so the action force would be the bat hitting the ball, and the reaction force is the exact opposite, the baseball hitting the bat. So I hope you guys noticed a trend with all of these. There's an action force and a reaction force, and they're all very similar sounding to each other. Like the bat hit the ball hit the bat, the bottom hit the chair hit the bottom, the finger hit the phone hit the finger. That's how it is always going to be with these forces. And they can be as simple or as complex as you can think of. Anything from just walking on the ground, your foot pushing a force down on the ground and the ground pushing a force up on your foot, or A rocket taking off. The force of the engines pushing on the ground and the ground standing strong and helping the rocket be pushed up off of it. All right, and sometimes the examples are a little bit harder to see, so let's check out this video.
Barnes throws one to deep right field. Puig is back at the wall. He leaps.
Ouch. All right, so he ran into a wall. How could the forces be equal? Oh, yikes. Well, the force applied by the player is equal to the force applied by the wall. The result, however, is a little different. The wall is strong, the wall is heavy, the wall is not moving because it is so much heavier and larger than the person. Actually, the size of it doesn't matter. It's really the weight. That baseball player does not weigh nearly as much as the wall would. Therefore, the result of those equal forces, the person hitting the wall and the wall hitting the person, the result of that is going to be different. Because the wall has such a much bigger mass than the player will have a resulting acceleration from his force, or from that reaction force. But the wall's not going to accelerate because that's not enough force being applied to it to make the wall actually move. So now when we get into the nitty-gritty details of this law, we we do see how Newton's second law is really, really intertwined with this law. That with the forces, the result of those can be in an acceleration, which we've already practiced with those calculations. All right, let's get some practice for you guys now. All right, question 1. While driving down the road, a firefly strikes the windshield of a bus and makes a quite obvious mess in front of the face of the driver. This is a clear case of Newton's third law of motion. The firefly hit the bus and the bus hits the firefly. Which of the two forces is greater? The force on the firefly or the force on the bus? I want you guys to make a prediction. All right, your answer. Trick question. I'm sorry. So each force is actually the same. Okay, remember the force of the person hitting the wall and the wall hitting the person? The forces are the same there. The result, however, is going to be different. They will be acting in equal and opposite directions, but because the mass of the school bus is just so much larger, it's not going to do anything. And the firefly is so tiny. It's not going to end up very well for the firefly. All right, let's try another question. Many people are familiar with the fact that a rifle recoils when fired. This recoil is the result of action-reaction force pairs. A gunpowder explosion creates hot gases that expand outward along the rifle to push forward on the bullet, consistent with Newton's third law of motion. The bullet pushes backwards on the rifle. The acceleration of the recoiling rifle is, all right, I want you guys to decide if it's A, B, or C. All right, let's check your answer. It is B, smaller than the acceleration of the bullet. Okay, so the force on the rifle equals the force on the bullet. That is consistent with Newton's third law. Yet the acceleration depends on both force and mass. So the bullet has a greater acceleration due to the fact that it is a much smaller mass. All right, one more. In the top picture, Kent Budget is pulling upon a rope that is attached to a wall. On the bottom picture, Kent is pulling upon a rope that is attached to an elephant. In each case, the force scale reads 500 newtons. Kent is pulling, all right, read through A, B, and C. Pick your answer. Correct answer is C. Same force in each case. And we can actually literally see it. It says 500 newtons. 500 newtons. Newtons is a force unit. If it's literally telling us that it's the same, the forces have to be the same. The result, of course, though, could be different, like we've been saying. Okay. All right, and that is it for today. Please check Google Classroom for your next activity.